Okay, so I'm now going to introduce our first keynote speaker, Alex Dimakis. He's a professor at the ECE department here at UT Austin and the co-director of the National AI Institute on the Foundations of Machine Learning. He received his PhD from UC Berkeley and his and a diploma from the National Technical University of Athens, my city of birth. So that's another commonality that we have here. He's working on deep generative models and machine learning with applications that include image generation, super resolution, and medical imaging. So thank you for taking the time to be here.
All right. So I guess you can hear me. I'm gonna maybe move the mouse around too. So I'm Alex. I'm a professor here in UT Austin. So I didn't travel. I am coughing a little bit, but I don't have COVID. But I don't have a toddler who gets sick every day. Hopefully it's not COVID. I'm actually feeling fine. We have an institute here in UT Austin, the Institute for the Foundations of Machine Learning. That's an NSF institute, and I work in artificial intelligence and machine learning as my research area. I will be talking about work we have been doing with my research lab and also many other collaborators here in UT that are listed here. So the point is neural networks that can imagine things, and how is that useful and fun. So these networks are called generative models or deep generative models. And the way they work is they take as an input a random noise seed, basically some random numbers. And I don't know how many people here are computer scientists or computer engineers. I suppose not too many. So please do ask me questions, and it's more fun to make this interactive. But practically speaking, it's a Python function, right? You just download some Python thing and you say, hey, generate an image. The seed is 2731. So you just list 100 numbers and it's going to spit out an image. So they generate images and has been trained on a domain, a training set of real images. And the most famous very recent version of this is what's called text conditional generative models. Has anybody here heard of DALL-E? Do you know what DALL-E is? Who has heard of DALL-E? I want to see hands. So, okay, I'll show you some examples of what DALL-E is. And it's a text conditional generative model. And somebody has entered the room, I can admit them. Should I admit them?
There is someone outside doing that, but yeah.
Very good, very good. I got you. So they generate images. Let's recap on that point. And I need to close. I don't know how to close this, even though I've been using Zoom and teaching for a while. Does anybody know how to do that? No?
Yeah, I got you. You let me let go of the mouse for 1 second.
Okay. Okay, there we go. All right, so these are networks that are called classifiers. A classifier is a network that as an input, it takes an image like this cute cat, and as an output, it tells you what it is, all right? So it tells here that this is a cat with probability 0.7, 70% a cat, maybe 1% airplane, maybe 1% banana. These networks do make mistakes, but they're very good right now. So if you want to download the Python script that you upload images and it tells you what they are, this is kind of a problem that we're very close to solving with artificial intelligence today. It was not the case 6 or 7 years ago, so this has happened very recently. But it's not what I'm going to talk about. What I am going to talk about is another problem, that is generators. Generators take as an input some random seed, as I said. They have some weights here. This is trained on GPUs for a very long time on a lot of data. And the output is a generated image. And this image, as you train it, this is actually us training a neural network, a generator in my lab. You can see that after a while, it starts producing images like this. And I want to emphasize that this person, I don't know if you know her or not, but she's not a real person, okay? This is the dream of this neural network when I fed in the numbers 1, 2, 3, 4, 5, up to 100 as the seed. And this has happened in the last 5 years, and we're able to generate, yes.
What do you mean when you put in the numbers? Like, do the numbers refer to certain?
So what you do is there's a Python script, there's a program, and you say generate, and the seed is 1, 2, 3, 4, 5 up to 100. It spits out this. If you put different numbers, it's going to spit out a different image.
But what do the numbers point to?
They mean nothing. So
They mean,
they
okay.
mean nothing. They are just a random seed. It's just a source of randomness for this machine to crunch. It starts with some random independent numbers. It crunches them through these weights that it has learned, and it spits out natural images. Thank you for the question.
Sure.
All right. So this started in 2015. These were called GANs, generative adversarial networks, and there's many other things now called diffusion models, autoencoders, and so on. So they have gotten pretty good. All right. So this, I need to close again, but now I know how to do that. Hide the floating. There we go. So here is one. Actually, this is even a website, so you don't even have to download the script. You can go to the website, thispersondoesnotexist.com. And every time you refresh the page, you see a face of a person, like this person. And this person is not real. It's just a dream of a generator that's called StyGAN2. This was trained by NVIDIA, and it was trained at a great cost. So the cost, the computational effort, and the amount of data that goes into training these things is in the hundreds of thousands of dollars typically, or even possibly millions of dollars. Okay, the compute is insane to train them, and the amount of data is insane. These are trained on public data sets of pictures of celebrities, usually, or other data sets of pictures that we have all uploaded on Facebook and so on. So then this goes on, as you can imagine, and I need to click on the next slide now. There we go. This aerial photo does not exist. That's another website that you can go to, and you're going to get a generated image of an aerial photograph like this one, and it looks pretty realistic. And it starts to sound a little silly, perhaps. And then there's this chemical bond that does not exist. That's another. These are actual websites. Like you can go, and every time you refresh, you will see it will generate a bond. Yes.
Is there copyright on any of the images?
Great question. The legal issues are a mess. Nobody knows, and it hasn't been decided. It will be decided, I believe, once cases go to courts. It's very confusing because this could be literally just like this person here could be a blending of actual people who are on Flickr or on public data sets. I don't even know what the licenses are. When you upload an image on Facebook, I don't even know if you own the copyright of that. You probably don't. Nobody read those agreements. So yeah, it's a very good question. It's going to get very complicated very quickly because this is not literally copying patches of existing people. It's blending them in very interesting ways. And we know that because we're spending a lot of time analyzing if it's literally just memorizing some normal faces or something more. And it is doing something more.
Excuse me, so the randomness is a selected randomness, no? I mean, it chooses from a set of images from persons, and then
the input
sends them to that. I mean, in the input is random from a set of given images.
No, the input is just some random numbers that you are typing. You can literally type any numbers you want. It's going to generate a different face. Think of it like some source of variation, some source of randomness that is fed into the system.
Okay.
Great. So this, you can do this with chemical bonds. This is not by the way, this is not a real molecule. It probably cannot be constructed in reality, but it doesn't matter. This neural network saw a bunch of real chemical bonds, and now it generates fictional items that seem to have the same statistics as the data that has been trained on. Okay. Now, then it got more fun in last year with what's called DALI. So I'll show you that. And I know how to hide this thing again. No, not hide the names of annotations.
You have to hide that. That's it.
There it is. All right. So again, DALI 2. You can go to OpenAI website right now. And I think you put your credit card in. I think you pay 1 cent for every generated image. You type a text. So the prompt I typed, I was giving a talk in Nafplio, which is a beautiful city in Greece, if you know. And I typed this text, please generate a painting of the Greek city of Nafplio. And it generated this. It's pretty good. It kind of looks like Nafplio. And then you can go crazy and ask it to generate an image like this one, a painting of the Greek city of Nafplio in the style of Klimt. So it knows who Klimt is, for example. And I think that's pretty plausible, right? You could say that, I don't know in a blind test, if I give you a bunch of images like this by artists you don't know versus real artists, I don't know if it would pass what we call a Turing test, a visual Turing test, where you cannot tell if they are real images by artists or generated by this network. This is generated in 2 seconds, right? You can put any prompt you want. In fact, yesterday at midnight, when I was making this talk, I went there and I typed, "Here comes the metaverse." And it generated 5 pictures, and I picked this one, which is quite interesting. Okay, there is some amount of cherry picking you can do here because the machine spits out 5. You pick the one you like the best, and then there's a whole new type of programming that is emerging, and that's interesting to artists. That's called prompt engineering or prompt design, where you start messing around with the text to get what you want, right? So people, for example, do. So then I did this. I said, a retro white fairy monster in the metaverse. I played around with a few prompts and I found this like fine cute. Now, you can keep describing your image. You can say a retro, comma, high quality, comma, a high quality rendering, comma, in the style of Klimt, and so on. So you can mess around with the prompts, and people are spending a lot of time right now designing these prompts and interacting with this machine to get the images they want. And it's fantastic. Like it's actually shockingly good. All right. So what I'm, an electrical and computer engineer, and I am very interested in art as a hobbyist, but I also want to do like things that are useful for science and engineering. So this has been my interest is, okay, these networks are great, but can we do something useful for maybe science or engineering with them? And one thing that people do is they generate fake pictures, like for this person does not exist. You can go there, generate 10,000 fake images of 10,000 fake people, and you use them to create fake LinkedIn accounts. People do that, right? So that is one use, but it's not a good use, right? But it is definitely a use of this that this has found. But my main message in this talk is that beyond the fact that you can do that, I want you to think about a different message, not just to generate fake images and look at them, which is fine, or it can be used for art, which is also as an artistic tool, which is also extremely interesting. But I want to say something much more than that. They can be used to solve what I call inverse problems, all right? So inverse problems, the most easy to explain directly is the problem of colorization. Colorization is the following problem. You have a black and white picture of an old photograph, right? And you want to colorize it. You don't want the network to dream of some random color image. You want to colorize your own image, right? So this is, I think, the most interesting type of problems where you have an image that's noisy, or maybe somebody took your old photograph of your grandfather and ripped part of it out. That's called inpainting, right? So we can use these models, these machines, not to generate random images, but also to improve our existing images, okay? And we are working on this, for example, in the problem of denoising, the most classic version where somebody spilled coffee on your photograph and you want to make it new again. Compression, which is another flavor of problems that are closely related. In painting, I will show you. Super resolution means you take a picture that's too low res, you want to improve it. These kinds of ideas are going to get in all kinds of imaging systems, including your phones, right? Because your phone camera is becoming driven by AI. Also in TVs, actually use super resolution technology. I think even today, not the most latest and greatest, but even today they use upsampling techniques to increase the resolution. So MRI is an area that I'm working on, magnetic resonance imaging. But again, it's like a subsampling problem. You want to accelerate the time it takes to do a scan. And I'm going to show you some examples very quickly on that. So directly jumping into results, here is my friend Vijay. I need to hide this. So this is Vijay, who's a professor in Michigan. He invited me to give a talk there. I went to his website and I downloaded his picture, which you see here. It's 225 pixels by 225 pixels. And then I removed a huge chunk of pixels in the center, right? This is called inpainting. Somebody spilled coffee on this image. They want to fill in the missing pixels. And for free, we're also going to do super resolution because we're going to go from 200 by 200 pixels to 1000 by 1000, okay? So running the algorithm that I showed you, and the key idea relates to these random seeds that you've been asking me about. These are like little knobs, and when you put them in a random position, it generates a random face. But now I am searching in these knobs so that the generated image looks like Vijay as much as possible, right? So I have an algorithm to search how to tune these knobs. That's the key idea of the algorithms that we are developing. And using our current techniques, we get this image. This was in 2017. Now, if you look at this, you see that it is knowing that, so can somebody hide the float that keeps popping out? Is there...
The tech man is, I'll see if I can.
Yeah, so it's easier if somebody else hides it, yeah. So this image is the one that is generated, and I want you to notice a few things about it. It is pretty good. It has learned that humans have two eyes, right? Roughly symmetric. You have 1, 2 ears, and so on. It's actually not perfectly symmetrically copying the mouth. Actually, it's copying it in a non-symmetric way, which is interesting. And the other thing that it is also okay. There we go. Thank you for that. So you can also see that this image is high resolution and it's pretty good. But if you know VJ and you saw this image, you wouldn't say this is VJ, right? And the other thing you may notice is that this is actually a white guy, right? But VJ is not, right? So you can also see that the bias of the neural network is kicking in here and it's actually changing the race, which is a huge problem. So they're using newer techniques by changing the expressive power of these generators so this was 2017 in our paper that's called the CSGM algorithm. Updating our algorithm, we were able to get this result by not only changing the initial knobs, but also some internal knobs in this generator. And then even deeper in the network, we're able to get this image using 2021 results. And here you can see that this is very close to the original image. This is still generated by StyleGAN2, but with a better algorithm. And now it's actually matching the measurements, as we say, or the observations much better. So the simplest problem, very quickly, how we do this is, okay, I took my picture here. I have my generator here. This is the generator, this network trained by NVIDIA called StyleGAN2. And I want to set the knobs. See, these are the random numbers that I want to set so that the image is not just some random image, but actually looks like me. Right? And there's some math here that, unfortunately, there's this caption that's also terrible because of my Greek accent. As you can see, my great accent. Turn this off. I think it is a disservice to everyone because if they try to read this, yeah. Anyway, so my point is there is an algorithm that we have which basically updates the knobs and generates an image that tries to match my image. Does that make sense? So it's called gradient descent in the latent space. And if you run this algorithm, you get this guy. And this guy kind of looks like me. He's a little older. He's a little more sad, maybe. He doesn't exist, okay? It's not any other person. You won't be offended. So you can see that the network is doing a decent job, but it's not expressive enough, as we say, to truly match all real humans very well. But and the central idea I want to communicate is we are not just asking the generator to dream of some random image. That's cool, but you can do other cool things. We are changing the input knobs so that the dreamed image matches the measurements. That's the central idea of our algorithms, right? And doing that, you can see the bias again. Now, instead of just generating an image that looks like my image, you can solve in painting with essentially the same idea. But now you don't want the generated image to look like this woman with a huge black square in the center. You want to generate a woman that agrees with these pixels only on the pixels you are observing, right? So you can change the loss function, and it's essentially the same algorithm, but only on the observations, and you get this image. And it's pretty good. It's not perfect. It's not a state-of-the-art technique for in painting, but off the shelf with no effort. Because this network was trained to know the statistics of humans, it can fill in missing data. And then it can also do super resolution. You have a blurry image. You're not going to ask the network to dream of a blurry image because the network does not and should not dream of blurry images. The network should dream of clean images, right? So the way you use the network is you say, I am going to generate an image so that after it has been blurred, it agrees with my blurry observation. So that's essentially the idea again. And if you run the same algorithm, you get this deblurring, which is pretty good, but this is, again, using 2017 neural networks, which are ancient by the rate of progress we have in this field. If we do this again today, it's much, much, much better. I'm going to show you some results in a minute. So this is the general algorithm we proposed. And it's basically updated the knobs to satisfy the measurements. So The problem that I'm showing here is that the network has its own biases. This is one of my tweets that was probably my most successful tweet, where I was joking that if we use a deep learning algorithm to do MRI reconstruction, by the way, almost the same problem, instead of reconstructing an image of my face, you're gonna construct an MRI image, and it's subsampled in Fourier space, but it doesn't matter, like the math is essentially the same. So you can try to reconstruct MRI images with essentially the same idea, but you need a generator that knows the statistics of MRI images. So if it has been trained on the internet where it's full of cats, it may start dreaming of cats everywhere. And here I'm showing that it can dream of a cat in place instead of your kidney here in this, this is kind of just a fun thing I did. It's not a real, this didn't really happen. But what can really happen is that you've trained your generator on a bunch of images of people who have various types of tumors. And there's one particular rare type of tumor just isn't in your training data. So your generator doesn't know how to dream with that thing, right? And now you have patients who are actually getting the tumors having a different type reconstructed, and that has terrible clinical implications, right? So it's extremely important to look at the biases of these generators and how they can affect, for example, the race, the identity, or even clinical applications where if you want to use these things. And by the way, there is no doubt in my mind that these networks are going to be used in all these applications because they're just so powerful. So if you don't address this and say, oh, we're not going to use them, that's not going to fly. So you have to address this problem. So the way we found to address them is as follows. So I'm getting a little technical here, so I'll just roughly explain the idea. You start with my picture, target Y, and you just run this, optimize the knobs, and you get this sad guy we saw before, right? But now I'm going to go inside the neural network, some internal layer, and I'm also going to update the internal structure, not only the input knobs. And if you do that, you get this image. This is from our 2021 results. And now, this is not my picture. This is actually a generated image by StyleGAN2 that really looks like my picture. If you notice carefully, it has blurred the background. It has created some artifacts around the eyes, but it is really generated by a neural network, which brings us to our question. Do I own the copyright of this image, or does NVIDIA own the copyright of this image? Nobody knows who owns the copyright of this image. Nobody knows what's going to happen in this space, okay? But this is just a generated image that agrees with my measurements, optimizing the latent space and then internal layers of StyleGAN2. So moving on, what happens if you go too deep inside the network? If you go too deep inside the network will start producing images like this, which are now too expressive. They have been inspired by human faces, but they are leaving the manifold of human faces in a Picasso type of way, right? So it's quite interesting that you can actually use these networks for artistic creation. Super interesting, I think, for design and for art. So if you make the network too powerful, you're going to make various collapses of the geometry that it has left, which is quite interesting, I think. So just in painting. So let's go over this. This here is a real person. He's Stefano, he's my friend, and he lets me do this stuff to his image. So this is a real picture, the ground truth. And what we observe in this is this problem. We observe this here. This is an in-painting problem, but not a big square missing. It's actually a ton of pixels are missing. So this is the image. Every pixel you see black is literally a 0, 0, 0. It's missing. So now, if I told you from this image to recognize who this person is, I don't think anybody would be able to do that. So running our state-of-the-art algorithm, we get this result, whereas the previous state-of-the-art algorithm, which was called Pulse, these are all using generative models, is reconstructing this image. And this image is very good, but it's not Stefano, okay? So it is a very realistic human face, but I don't think you would recognize that it is this person. Whereas arguably from our result, you can still recognize. And here's another similar result. The input is this. This is a dust of pixels. It's 1% randomly observing pixels, okay? So from each pixel, you flip a coin, and with probably 1%, you keep it. Otherwise, you remove it. And then this is the reconstruction we get. This is the reconstruction the previous state-of-the-art algorithm gets, and this is the ground truth for this particular observation. So when my students showed me this, and they said, we get this result, I said, there's no chance you're getting this result. You have a bug in your code because I don't believe you can reconstruct this person from 1% random pixels, but you can, okay? So right now, and our code is public, by the way, and our models are public. If, it's very easy to try this with your own images. If you can use a Colab in Python and upload your own image and try this. And it's shocking, okay? So right now, we're going to reconstruct images of people with very, very, very few observations. And it can be subsampling, like random pixels, or blurring, or low resolution, and so on. So
I find that absolutely terrifying.
Yes.
For marginalised people on the internet who purposely conceal their identities.
yeah, if you think you're concealing your identity by blurring your picture, that's not going to work.
Yeah.
So yeah, that's very important to know. Yes.
I also think there's an interesting cognitive question here. How would you define this as imagining?
Yeah, I have a script. I type some numbers, it spits out an image.
Yeah, but there's a determination to what it is supposed to create. So it's purely cognitive question whether this is imagining or not.
Yeah, it is just crunching numbers. All right, it's just crunching numbers, but maybe so are we. I don't know. I'm an engineer, so I'm a practical guy. But yes, I don't know. It's a good question. Yes.
No, actually, it's terrifying at the same time. It could be a groundbreaking in terms of criminal case. So it's really
Who do we criminalise on the internet?
what I'm saying is, there are a lot of civilian cameras, CC cameras everywhere, and you say the camera caught a criminal of doing a wrongdoing, and it was blurry. And with this technology, we can just, clarify that image too.
It's going to get more terrifying in a minute. so yes, these are all good points, but it's actually even worse than that. So let me show you the bias problem. But thank you for the conversation. And so the plan here is maybe 5 or 10 more minutes I talk, and then we have a conversation. The garden is here. This is and we don't have to rush. Okay, okay, good. So this is terrifying. First of all, if you think you are anonymizing yourself by blurring or pixelating your image, you are not, all right? But if you're going to start arresting people using this technology, you're going to find out, as people have found out already, that this is a terrible thing to do right now because of the bias. So let me show you that. So you can also use it for denoising, just old pictures or any grainy pictures. You can remove noise, of course. And you can also use them for super resolution. So super resolution has two flavors. It can be a blurry image, or it can be a very low resolution image, like a 20 pixel by 20 pixel image. So you're just trying to zoom in, for example, in a person. Now, these people are actual real people that you all know, right? So this is Barack Obama, Samuel Jackson, and this guy from 300, the documentary, right? So you know who I'm saying. So I forgot his name. That's right. Okay. So these are real images. Now, what our network is observing is these images, okay? These are very, very, very blurry versions of the original. Our network, just to be clear, is certainly not observing or has not been trained on those images, okay? So this is the observations. And if you run the previous state-of-the-art method, which is called pulse, to deblur them, to do super resolution, you get these images. And particularly, I want you to look at this image here. Stop talking. Please go. Anyway, this image is very famous because it's called White Obama. Right? Because people saw that when you upload a blurred image of Obama, it actually produces this white guy who's now known as White Obama. So if you Google White Obama artificial intelligence, you'll find this, okay? So our method is mitigating this bias, but still, we cannot guarantee, we don't know how this relates to images of people who may not be in the training set, and how much the training set is affecting all those issues. It's a huge problem. So the bias issue became viral on Twitter in 2019 when they created Pulse. And this was on Twitter. They said, here's a face depixelizer. It's free. You just go on a website, upload this image, tiny image, and we're going to give you this image back, right? Amazing, right? So, it's free and available for anyone to use. So this is the input, this is the output, okay? And then somebody went in and uploaded this image of Obama, and they got White Obama, and this got viral, and there was huge conversations that kind of started started the research and the thinking about, okay, how is this created? We wrote a whole paper about this. Our paper is called Fairness for Image Generation. It was published in ICML, which is a machine learning conference. And I want to show you a little bit the results. The first row is real people. These are all real images. And these are images that are not in the training data. And it's crucial that these are not in the training data, because if they're in the training data, it could have just memorized, right? So these are real people. These are the observations, the pixelated images that the network observes. And these are the reconstructions of the previous method, Pulse. And these are the reconstructions we get, all right? Now, if you look at the previous algorithm, by the way, this algorithm and our algorithm here are not using the same reconstruction algorithm, right? So it's the algorithm that has changed. But the training set has not changed. So this is White Obama, and these are all other failed cases. So if you look at them, it is basically making people white, all right? So it's terrible. Okay, it's terrible in all kinds of ways. So if you replace the turban here with hair, it's doing all kinds. So the point is the White Obama fiasco wasn't a rare corner case. It's actually canonical behavior that these networks have biases, and they're introducing them severely in the reconstruction of the images. So in our paper, we went into even defining various mathematical definitions of what fairness means for imaging, for image reconstruction, because you have to think a little bit about, okay, if the data set has, let's say, 60% white people, 40% black people, and then your reconstructions, what exactly do you call fair? If your algorithm is matching those statistics, is your parity, is that fair? Because then, so there's all kinds of, you have to be careful about your definitions. And we show in our paper that two very reasonable concepts that you may think about are incompatible with each other. So it's impossible. So you think of two definitions, they're mathematical, so I don't want to get into them now, but you think of two definitions that if I tell them to you, you say, okay, this sounds reasonable, and then you realize that it's impossible to have both of them at the same time by any algorithm, okay? So there's issues like that. But there is another issue that I want to tell you that's a mathematical problem that I think is easy to understand. So everybody on Twitter was asking this question. Okay, it's a data set problem. The data set had only white people or had 90% white people. That's why the generator only knows generate images of white people, so it's going to make everybody white. Okay, so then there's a solution to that. Make a better data set, right? And what we are proving in our paper is that it's not only a data set problem. Of course, there is a data set bias, but the algorithm itself is amplifying that bias. The algorithm is called map inference maxima posteriori. And I will try to explain to you the mathematical reason why maximum likelihood and maxima posteriori is indeed amplifying bias. All right. So there's a little bit of math, but here's the central idea. I have a coin, we're going to play a game, all right? And I have a coin that comes heads with probability 60%, all right? And I'm going to flip this coin here 10 times. So I'm observing here a sequence, heads, tails, heads, heads, tails, heads, tails, okay? It's a hidden sequence. You don't see my sequence, all right? But you expect how many heads? 60%. You expect more heads than tails, right? Okay. Now, the way you play this game is you take a piece of paper and you write down 10 outcomes. You can write heads, tails, heads, tails, heads, tails, heads, tails. You can write any sequence you want. And you win this game if you match my sequence, all right? You want to write a sequence that has the maximum chance, the maximum likelihood of agreeing with the real sequence that you don't get to observe. All right. What sequence are you going to write down on a piece of paper? So one thing you could do, so the game is you have to guess a sequence to maximize the probability you are correct. And you could do something like this. You could guess heads, tails, heads, heads, tails. So some sequence random that has about 6 heads and 4 tails. Does that make sense, right? This is what's actually going to happen. However, if you know probability, you will realize that the best sequence you should play, the sequence that's maximizing the probability you are correct, is all heads, all right? So that is actually the maximum likelihood sequence. The maximum likelihood sequence is all heads because there's a little bit of bias every time. But if you want to find the maximum likelihood solution, it's always heads. That is a problem of the algorithm because the algorithm sees a blurry face, and it is so obsessed about getting it right, because that's how the algorithm is trained, right? Maximum likelihood means I want to maximize the probability, the chance that I'm correct. So that's what I'm trained for. If there is a 60% chance this is a white person, I am always going to say white person, right? If I see 100 blurry images or 1,000 blurry images, and I'm like, okay, this is 55% white person, I'm going to produce 100 white images, right? Because that is the most likely thing. So a tiny little bias in my training data is going to be amplified by an algorithm that is obsessed, so to speak, of getting the thing correct. So maxima posteriori, is maximizing that, so it always predicts the majority outcome. The previously used reconstruction algorithm, therefore, was actually amplifying the bias, and in our paper, we explained that you should not do that. You should sample from the posterior, which means, in practical, in our game, you flip your own coin that has 60% heads, 40% tails. You write down that sequence, and that's your prediction. That's not going to be maximizing the chance, but it has some fairness guarantees that we prove in our paper. Okay, so that's kind of the story of fairness, and we can dive into it in our garden conversation in like 5 minutes if you want to talk more about it. Very briefly, just for me to wrap up the talk, we applied the same ideas for magnetic resonance imaging. All right. This was published in 2021 in EURIPS, which is another machine learning conference. In MRI, I don't know if you've had an MRI, you get in this big magnet and it's like, it makes a lot of noise. And then it's literally observing parts of your body. It's observing projections actually in the Fourier domain. That doesn't matter. You can think of them as observing pixels. But because if you may want a high resolution scan, it may take 30 or 45 minutes for a scan in an MRI machine. So our goal is to do something like in painting. Instead of observing all the pixels, observe 1% or 5% of the pixels and do the completion using an AI generative model. And for example, we were targeting 4x or 12x faster scans. And that means if you can't do that, you can scan 4 times more people or 12 times more people, or you can reduce the cost of the scan by 4 times or 12 times, because the cost of the scan is primarily the machine utilization, right? And you can also do things like scan babies, because babies do not stand still for 10 minutes so that you get a useful scan. But if you could scan them in 30 seconds or 1 minute, you could get possibly a useful scan, right? So there's a lot of applications of accelerating MRI. So we use the data set. So in order to do that, we need a generator that dreams of MRI images. So we need to see a lot of MRI images in the order of 10,000, for example. By the way, if you are an artist and you want to make a generator that generates cars or bottles of whiskey or anything else, you have a data set of 1,000 or 10,000. Usually, actually, even with 1,000 images, you can actually make your own generators now. And it's easy to do that with code that you can find online. So for MRI, we trained one, and we matched the state of the art compared to other methods. But the most important thing we found is that it's more robust to changes. The problem always is that if you change the scanner calibration, or you change the patient, or you change what you're scanning, the method has to be robust to all those changes, right? It has to be, otherwise it's going to create all kinds of artifacts. So this is very quickly our results, and our algorithm is pretty good. It's not the best out of everything that currently exists, but it's the most robust thing that currently exists. And I can dive into more details if you like. So recap, generative models are neural networks that can imagine stuff, okay? Or at least that's how I think about it. They can be used as priors for all kinds of inverse problems, right? Like the ones I've been talking about. And they can be combined with other networks to guide generation in interesting and useful ways. There's countless applications, as I said, medical imaging, computational photography, all kinds of seismic imaging, geological imaging, and all kinds of science and engineering applications. And I think also maybe you have other ideas that we can discuss. And overall, I think this will be a big part of the future of AI, and it's extremely interesting and also a little scary to think about. So I'll stop here. If you're interested in my papers, this is my homepage. These are actual research papers we have published in space, and I'll be open to discussion. Thank you all very much. This one?
Yes.
Yes, yes, yes.
So thank you for a wonderful, thought-provoking presentation. Open it to the floor. We have questions. The first question, I'm going to ask the first question. And it's your last point, which is the future of AI will be unsupervised.
Yes.
You know, one of the things that is the kind of tension between is it the machine or is it us? And sometimes when we kind of lean towards it's the machine, then we hide the fact that there's humans that are defining these algorithms. And so one of the things that we've done in the, you know, thinking about food is that on the package of every food, it says all the ingredients so you know what kind of poisons you're putting into your body. What is it in the landscape of transparency of algorithms? Well, we know what are these machinations or these things that go behind the production of not just images now, but of what we see, how we see, political communication. This goes to the core of it.
Yeah.
What do you see as the regulatory landscape, which is not just copyright? You know, kind of what we think is that IP may be the way to engage it, but you know, what's the politics of transparency around these, and what do you do to, you know, open up the ways that you intervene in the interpretation of these data sets?
Yeah, good. Okay. First comment. I need to clarify the word unsupervised. All right. So this is a very important word. It means something very specific in AI. All right. It doesn't mean the general concept of, oh, my kid is unsupervised and, you know, she's going to light the house on fire. It means a very specific thing in AI and ML. It means the following thing, but it relates to the problems you said. But let's clarify supervision first. In machine learning, supervision means labeled data. All right. So if you create a data set that has images and it says, here's an image of a dog, cat, dog, cat, dog. So that's how we used to train these classifiers that I showed in the beginning. People were manually labeling millions of images, okay? So using crowdsourcing, ImageNet, you may have heard of ImageNet, which is a labeled data set. That's supervised learning because people actually manually labeled millions of images and they annotated them with labels, okay? Now that thing works. That's all. Most of the practical progress that you see in AI is driven by supervision, supervised learning, because that's easy to do if you have a lot of labeled data. But the real problem is humans, we know, do not learn by pointing. Like I don't to a kid, I don't say, you know, car. Like I don't need to show 20,000 cars to a kid to understand what a car is. Maybe I show one car or two, but then they have the internal representation of the concepts to understand, okay, that's a car. If a car looks like this is a truck, if a car looks like this is a formula car and so on. So we have representations that allow us to do what's called zero shot or few shot learning with very little supervision, or which means with very little labeling. Generative models are unsupervised methods because you show them a lot of images, but you don't need any labels, right? So that's basically what I mean. Now, the problem you pointed to, however, the problem of transparency, accountability, and fairness in machine learning is a huge problem. And there's, again, a lot of people who are thinking about how do you define transparency, how do you regulate AI. So I'm in a commission where we try to discuss those things and propose ideas of what is sensible. But on the other hand, by the way, another thing is if you regulate too much, you could actually make progress much harder, which means other countries may make the progress, right? Which is another thing you have to think about. And the second issue is if you regulate too much, you may actually not produce something very useful. And it's not clear to me which forms of regulation. For example, in GDPR, I visited Greece recently, and many of you, I think, may have experienced GDPR in practice. I know GDPR is a big complication for a lot of people who develop software companies to comply with the GDPR regulation. So I don't know how much GDPR is helping, for example, versus how much GDPR is creating problems to people who build software tools. And if you make it very difficult, then you're only allowing the massive company to comply and you're making it impossible for a small startup to be able to compete. So that's another issue. So it's not that, oh, it's easy to okay, let's regulate the hell out of AI and make everything illegal for a number of reasons. So it's a very complicated story, and we are all thinking about it carefully. Even defining correctly transparency, accountability, and fairness is something that you have to do precisely. And many people are working in the space. Yes.
Many of you in this room probably aware of the huge controversy in September, Colorado fair, the art competition. This guy won a blue ribbon by this image generated by Midjourney. And a lot of artists are saying, oh my God, this is not good, because this AI learned deep learning by all the data that's collected online. So all these artists, feeding their artwork online, like Facebook, Instagram, all that. And this AI learning all that and generated this image. So, but I don't know what to think about this yet.
Yeah.
But some say when photography, like camera was invented, this type of discussion is ended, But some say, no, there's a fine line between artists' creative, work versus AI generated, through this deep learning should be differentiated. Then this guy who created this image, Alan, I don't remember his family name, but he said he did not do anything wrong. He did not deceive anybody. He just openly said, this is, like Midjourney generated image.
Yeah.
What do we have to think about this?
Yeah. So I can tell you my 2 cents. I don't know, obviously. I think that, what is it like? Good artists, great artists steal. Is that the quote? Like, good artists copy, great artists steal. This allows you to steal allows you to steal on a different level, right? So, because you're like stealing the whole internet. So I don't know. All right. So I don't have any training in art or in art ethics or in the topics that would be able to intelligently speak about this, other than I can tell you what can be done. All right? And I can also tell you what I think will happen, but I definitely don't have anything intelligent to say about art or how credit is distributed in art or legal issues. Also, I don't have anything on the legal issues. I can tell you that my current understanding is that nobody knows what's going on. But what I do know is that these tools are incredible. And I don't think that we should think of, so let me spend a little bit of time with that, because I think that is very interesting. So you can literally go on DALL-E on the website, or Midjourney, and just type your prompt, right? And it will spit out an image. But I think the most interesting ways that this will be used is not just generate an image and use it, rather interact with the machine in the same way you interact with your camera or your paintbrush, right? Or your Photoshop, right? So I think that the tools are changing all the time. These are incredible new tools. And I think that the most interesting thing, at least from an engineering point of view or from a science point of view, is learn what these tools can do, learn their limitations, and learn how to use them and interact with them. I want to show you something about interacting with the tools that I'm very excited about. That's also very new. So very quickly in my backup. Here is the thing. There's something called textual inversion. It just came out 1 month ago. And you can say to DALL-E or Midjourney, generate an image of a dog wearing a green hat and being in Sesame Street, right? And it's going to do that. But maybe you don't want to generate an image of a dog. Maybe you want to generate an image of your dog, all right? So then, but your network doesn't know your dog. It may know a famous dog like Lassie or something, but it may not know your dog. So the most interesting new development that I really found very interesting is you can create new words, new concepts, and then you can use these words in DALL-E or Midjourney in compositional language. So this example here is they took this, let me point it with my mouse here. You see this statue thing? So these scientists had this statue in their house, right? So they took pictures of this thing. They took 4 pictures of their statue. And then they trained what they call a pseudo word, S star. And then you can go on DALL-E or Midjourney or all these diffusion generative models and say, give me an oil painting of S star. Okay, so there's an AI algorithm that produces this pseudo word, and then you can manipulate this word in language. So you can say an oil painting of a star or an app icon of a star, okay, or Elmo sitting in the same pose as a star. And this, I think, is incredibly creative, because now you can compose concepts. You can create literally words for your own concept. You can go your own home, find an object, or even take pictures of your garden and then talk about your garden, right? And here's another example. They have this toy cat object. Again, it's some object they found at their house, and they took 5 pictures of it, and then they created a pseudo word for that concept. And then it says, oh, a painting of 2 S stars fishing on a boat. And you see, it creates this image using this object that they have in their house. So inspired by this is called textual inversion. You can Google it to find the paper. It's super new. But there's a whole community, by the way, right now on Reddit on stable diffusion. Okay, actually, let me talk about one more thing. DALL-E 2 is a closed source product. You can only use it through an API, but we can, like, the engineers like us want to get inside and look at the wires of this thing and mess around with it, right? Or even use it. I don't even know if you can use it for profit. If you want to make your own startup, I don't know if you're allowed to use DALL-E, for example. But so DALL-E is not open, even though the comment's called OpenAI, by the way. That's a constant joke we have. So it's still accessible through API. But there is another thing that was a grassroots competition that's called stable diffusion. That is open, it was trained publicly, and is available for everybody to use. So the big conversations about regulation, transparency, and so on, and also enabling the tools, is going to be, in my opinion, who has the tools and who can use the tools. Imagine if you were the only person in the world who can use Photoshop. Right? Imagine how more powerful you would be as a visual artist if you had these tools and nobody else has the tools. Or maybe everybody else gets a toned down version of the tools. Right? So the real battle, I think, at least one battle I think is crucially important from the engineering point of view, is making these tools open source, and open and accessible. And not only accessible through an API that somebody can just go on OpenAI website and put the prompt, but be able to access the network and the weights and mess with their internal guts. Mm-hmm. So stable diffusion is actually the most exciting thing in this space, because it's a public DALL-E. Think of it as a public DALL-E. So this was only done because there is a public DALL-E. Because if you try to do this with normal DALL-E, you would not be able to learn these secret tokens forwards. Yes.
My question builds off a little of what's being said there. So yes, when photography and film emerged, there was the same question of, these are new tools, artistic tools that have their own language and pose new problems. You could see it pretty much the same thing, I feel, about this. Now, but I do see kind of a dichotomy here, as in, on the one hand, it intervenes and it creates something. So we can look at it as a tool, a new art form, if you want to, take a broad definition. But I was thinking about, when you were talking about noise reduction, like, hey, could this be interesting to use, for example, in the restoration of heavily damaged, film stock? But then the question arises, isn't that at odds with the intervention by the program? Because what you want needs to be as close as possible to how the director imagined it, how the original image, what it looked like. And in this way, it seems at odds with the fact that at least the program intervenes and create somewhat of its own version of this. So you would have to, learn it to watch thousands of, silent films or old films that have been damaged. So I was wondering, to what degree is it an objective tool, and to what degree is it a creative tool?
Yeah, so the thing you said about film is already happening, right? Digitally restored old film is already a thing. And can be digitally restored in resolution or also in time. So sometimes it starts with tools that are not the fanciest AI tools, but they can do even super basic time interpolation and take an old film that's 20 frames per second and convert it to 60 frames per second. And some of them are better than others. and they're going to get much better. The frontier in generative models, you may notice I didn't show a single video, okay? So right now you can say, hey, generate a video of Mickey Mouse playing with Elmo in the style of Clint, right? A cartoon, a video, like, so we don't know how to do that yet. But I know that a lot of top research labs are working on this very hard. It's a very hard problem because the data is so much bigger. But I believe that we're also going to see generative models that do video, right? So I think the questions you're raising are inevitably going to appear in front of us. Now, I don't have anything intelligent to say about what should be done. I think that this will be done. And you know, it's definitely a very interesting space to think about. How and you're right, you're changing what the original creator had, but the original creator had this low-res film. So yeah, I don't know, but good question.
No, I'm thinking also just about the energy impacts, because the amount of computing that it would take to do this, right, is just exponentially as you need to put in more data sets and for the AI system to actually learn. That also has an energy impact. We already know our cloud computing is now 4% of our carbon footprint. It's going to be 8% in 10 years of our carbon footprint. So I'm just wondering how all of this plays into that, because I think other than just the ethical questions in terms of human impacts, there's also a huge ethical question in terms of energy impacts that's hidden that we're not talking about in this, right?
I do want to speak a little bit about that, and we have reviewed. I haven't written a paper on the energy impact of AI, but I have reviewed papers and have had conversations. I think that there is one part that many people are missing on this. So let's say Google, for example, trained this language model. By the way, language models are a huge other thing that I didn't get into, but the same, all these questions we're talking about, you can generate language, and generate essays and so on. So, this is the image, so I said I'm not going to get into that. But Google trained language models that are used now in search. And everybody says, oh, how much energy did it take? It took like this many billions of, I don't know, kilojoules or carbon. And it's true. However, let's say that it's making search 5% more efficient. How do you measure that? Because you measure how many times people do a search and then they do the same search with a slight variation. And let's say that is improving their search efficiency by 10%. You need to see how much that costs, because nobody came and measured how much the Google search is costing in terms of energy and compute versus the AI. So actually, what I haven't seen the comparisons of this. I did bring this up and had a conversation. So everybody says, oh, AI is la la la, but did any or blockchain? Everybody says, oh, blockchain is costing this much. But did anybody compare that to the banking system? Like, how much is the banking system costing? Because if you are proposing an alternative to, you know, international transactions, if it's costing less than PayPal and it's doing a bit better than PayPal, maybe it's not. So I think the correct way to, and this is obviously a huge existential problem for humanity, to understand our energy and our carbon footprint. But I think that AI is also a huge accelerator of a huge increase in efficiency in many of the things we do. For example, search is one that's search is huge, right? In terms of the energy consumption, it's insane how much energy we spend to just have Google search. It's hard to wrap your head about search, right? Because like I just go on Google and it just works. Like I just go on Google Maps and it just works. It's hard to wrap your head about how incredible that is. So, and it's easy to forget. So you say, okay, AI did this, but if AI is making that 5% more efficient, I think it's more than paying for its due. Because if you train the language model, now you're using it 1 billion times. So in my opinion, I am not actually worried that the language models or the generative models are going to be a problem. I think they may be part of the solution. So another example is in imaging when I'm recropping, right? Or I don't know if you, like many times in Photoshop, I want to take my picture of my dog and I want to put them on the desert, right? So I sit down and I'm doing that by a magic tool, right? So I want to set. Now I can do it with AI, and I click on the dog and it separates, right? So I just saved 20 minutes. So are you counting that as an? And if everybody's saving that, that's much more than the cost it took to train the cropping model.
Thank you.
Yeah. Yes.
So I have sort of like a technical question just to ask you to explain a bit more about the training side of things. So you said that, okay, there was two types of bias, right? One is through the actual training and the others comes from like the oversampling, like, you know, the sort of it gets the amplification part that's actually in the code. Yeah. I'm kind of interested in the first part. If you could talk about, like, because when the bias was that you were describing there was basically, let's say, a disproportionate amount of input was going in that was overrepresenting, let's say, white as opposed to black, right? So what happens, because this is the context like for biometrics, for example, where there's two types of errors that could happen, right? You either get a false match or you get a false non-match. And one of the things that plagues biometrics is that they can't reduce the error rate of one without increasing the other. So the more you train, the more you increase it. So I was wondering if you could elaborate how you avoid that in that particular kind of error rate.
Yeah, so all these models that you're seeing were trained on data sets that were collected primarily from the internet. And for example, the faces I'm showing you, there's a data set of human celebrities, and many people are using Flickr. I don't know if you ever use Flickr or all these image sharing databases. So if there are biases, and these biases can be something like obvious, like race, or something not obvious at all, something we haven't even thought about, that, for example, all the humans are looking straight at the camera, and then when I have an image of a person being tilted, it may not reconstruct. And that's a bias that is not something you may think about, or the lighting conditions or something like that. So a huge amount of effort is going in creating diverse data sets. Diversity can be diversity of race, diversity of lighting conditions, diversity of poses, diversity of actions. A huge amount of effort is going into this. And there's a big public initiatives where people are trying to collect and curate. So it's not just let's just crawl the whole web. And people have crawled the whole web, and there are data sets like that. But this is full of, it's messy, it's too messy. So then there's a huge effort of cleaning up those data sets, annotating them correctly, and a big part of our AI research, and I think even in the future, will be data set creation, data set curation, data set cleaning. So this is a huge part of our job, I think. Good question.
We have time for one more question. I know you've been waiting patiently here. Oh no. Okay, two more.
Okay. So I'm a little sleep deprived, so let me give this a shot here. I have a question. I have a twin question that's really sort of a forensics question. And one of them is about the role of AI in sort of searching for missing people, for example, or aging missing children. Yeah. But the other question is about this idea. I read somewhere that you can take DNA and predict what someone looks like, right? And so there's also a question of, you know, are there some potential forensic applications that would allow AI to not just search for missing people through a bunch of sort of predictive or imagining what they might look like in the future, but also thinking about how we might be able to take DNA samples, which now there's technology to even collect DNA from breath, right? So crimes could be solved by sort of reconstructing someone, which is terrifying. But is that like really far off, or is that something that you see starting to maybe come into focus as a result of some of the work that's being done?
Yeah, so on the aging, 100% totally here. There was a Reddit post, Reddit machine learning, which I follow, is very interesting. There was a Reddit post of somebody who created famous artists who passed away, Kurt Cobain, Elvis Presley, as they would be today. I don't know if you saw it. I saw it yesterday. It's fantastic. Yes. So 100%, we're all able to do that. Another related flavor of this for finding people that I think is interesting and terrifying is the fact that you can search massive amounts of video efficiently today and search, for example, all the cameras in London about finding a person. So that brings us to face recognition at scale. I'm not working on face recognition intentionally because it's like a super, taboo thing and rightfully so. But to the best of my understanding on face recognition, we are right now in the place where we can do pretty good face recognition at scale just from video. So That is a huge game changer for finding missing people, but also a lot of terrible other things to worry about. So, and there's also going to be a lot of countermeasures, I think. People may try to mask their identity. There's all kinds of AI tools, like there's hats with specific patterns that are intentionally designed to fool the face recognition algorithms, for example, and so on. So that is another part of it. On the DNA thing, I don't know. I don't think so. All right. So I don't think that, but I haven't seen the research, so I don't know. Yeah.
Thank you.
Last one.
Mine was more of just a comment to kind of go back to AI generated video. My graduate students are working on an experimental animation project right now, and a lot of them are kind of diving into the AI and generating images and then sequencing them to make new animations that way.
Yeah.
And another, if you guys are really interested in this stuff, Midjourney is a AI generating platform that is woven into Discord. You can get 25 images for free, and then it's like, I think $10 a month, and you could do like 200 images. And it spits out really serious, like digital kind of concept art and illustrative stuff. So.
Midjourney has a Discord server, and I know there's incredible. The other aspect of this, just quickly, there's a community aspect that is so much fun in these Discord servers or the subreddits and so on. It's because if you say, oh, now you will do AI art, and like I don't know anything, right? How do I start doing AI art when I'm like I can barely use Windows or something? So, but there's these communities that are incredible, and you can literally have 100 friends, and you can keep asking them questions, and they will actually respond for some crazy reason. So it's the community aspect is a huge aspect, I think, of this new creative world that's out there. And Midjourney, of course, is a huge part of it. Yeah. Great.
Okay, well, thank you very much.
Thank you.
Wonderful way to think about the tentacles of all this stuff as it weaves into our research and practice. So thank you very much. And thank you for explaining technical concepts in a very open way. So thank you.